So, really sorry if some of you guys are banking on this bonus. It's not true. What's it say? Propaganda activity. Okay. Is that a good activity? Okay. Too bad. So I want to I have a handout that kind of goes over section 1.1 ideas and a little bit from section 1.2. Just want to review really quickly. For a differential equation to be linear, what must be true? Yes?
It can't have an equation like sine of x or e to the x.
No, it totally can't.
It can?
Totally. It can't have sine of
Y.
y, right? Or, all right. So x could do all kinds of weird shit. Totally. Yes?
No variable can be to any other power than one.
Yeah, so y prime, y double prime, all of those have to be linear. They all have to be to a first degree. I like it.
So like things like trig or log, those would be nonlinear at the time.
If it's so this equation, this linear, give it away. This ODE is all day long linear. Why is that linear? Y is to the first power, y prime is to the first power, linear, right? If I did this, it's not linear, yeah. So that is kind of like the most fundamental distinction you can make, because linear ODEs are almost always crazy amount easier than non-linear ODEs, depending on a few things. But overall, holy shit. If you have a nonlinear ODE, you kind of go FML, and then you just do what you can. There are some forms of them that are not that bad, but overall they're worse. Is everybody with me? So linear, that's linear. Everything dealing with y must be to a first power if it's present, right? What about order? Order is pretty straightforward. The order of a DE. Yeah, it's all about the highest derivative. So if it was the fourth derivative is the highest derivative, blah, 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 that would be a fourth order. Okay. Maybe. But very quickly, what about this thing? Good. It's nonlinear. What's the order?
Second.
Good. Sorry, didn't mean to scream this. Do you see why some people want to see a fourth order?
Yeah.
But they're mixing up two things. How many derivatives am I taking? And I'm squaring that. I'm not taking four derivatives. Do you guys see that? So they don't interact that way. The square makes it nonlinear, but it's still a second, so it's a second order nonlinear ODE. Why is it ODE? What else could it be instead of ODE? PDE. What's O and P? O is ordinary, meaning not partial. I love it. I suck at charades, sorry. You're all like, just say word stuff. Oh yeah. All right, so with that in mind, I want you guys to try this out. It should be kind of quick, is what I'm hoping. Are the roads bad out there, or was it just bad parking, or was it just leave me alone, Jeff? I had a rough morning. I don't know. Could be anything. All right. Let's see. Focus button on this thing. It's concerning. There we go. There's my focus button. I like the doctor cameras. Like I don't do differential equations. All right, guys. So let's take a look. Let's take a look. All right, so very quickly, let's first knock out where are the PDEs. If I had this kind of problem with all these parts to it, I'd just find all the PDEs first, right? Where are my PDEs? Number 3? Oops. And 7? Anybody else? Okay. 3 and 7 are PDEs. All right, so let's come back. So everything else is an ODE. 8? Oh, 8's interesting. Why do I know that's not a PDE? Because look at the letter D. Is it all nifty, or is it just normal? Yep. 8 does have issues. I appreciate anybody who noticed that 8 is weird. Every other problem, the problem tells you what it's considering to be the dependent variable. But you all should know, from like doing one of your favorite things ever, which was implicit differentiation. Couldn't you solve for dy dx or dx dy? Do you remember that? And the easy thing is if you solve for dy dx, just flip every damn thing, and that's dx dy. Right? So every single one of these, the very first one, I could make that dx dy equals 1 over 10xy. Very quickly about it. I want this to really make sense. Does everybody see that? Number 1, if dy dx is 10xy, then dx dy is 1 over 10xy. Yes? Would it be linear in x if I consider x to be the dependent variable? No, because I'd have a 1 over x. I would have an x to a negative 1. It wouldn't be linear. But the problem has identified, we are considering y to be the dependent variable. Everybody with me? Y'all cool with dependent versus independent? We don't really use that terminology very, very often, but y is a function of x means y is dependent on what x is. Okay. So what about number 1? Is that linear or not? Totally, right? Every y piece, y prime, y, anything to do with y directly is being raised to a first power if it's there. Okay, so that is a linear ODE. What order? Yeah, I can't spell ODE. That's a really good example. All right. Linear ODE, and it's a first order. Linear ODE is the full classification. Fantastic equations of where to find them. Okay. What about number 2? I'm afraid to do anything. Let's see what happens. Okay. All the wrong lights went out. Oh, I didn't do anything. Okay, that's better. The second dude, is it? So it's an ODE. Is it linear? No. Non-linear. And what's the order?
Third.
Yeah, good. It's not fourth order, it's third order, because the most derivatives I'm taking is 3. So this is be third order, non-linear, ODE. I like it. This one we already identified as a partial differential equation. What's the order? First. Is it linear? It's a really weird question, but in this case, what's the dependent variable? Z. What's the independent variables?
X and Y.
Cool. X and Y together make Z, so they are the independent variables, and Z depends on what what we choose for them. So everybody with me? Okay. So PDEs always makes everything freakier for sure. So that's why you all should be like, thank God it's not PDE yet. What did we just say? Linear. Yeah. Number 4 is a really good example where the x's don't matter, because y is my dependent variable. That's an ODE. Is it linear? No. Yeah, y triple prime, y double prime, y, they're all to the first power. There is no y prime, so I don't care about it. It's not there, so who cares? So this is definitely a linear ODE. And what's the order?
Third.
Third. Kick ass. Anybody know what number 5 is physically describing? Second derivative of position, so that's the acceleration. Now, Which units? Does anyone know what units that's using?
Meters per second.
No, meters per second would be 9.8. Now, if you don't know this, you're fine. Some of you guys have taken some physics. Some of you guys might even be majoring in some kind of physics or engineering or something else. If you've never taken it, you might know this. But the 9.8 is the what? Yeah, the acceleration due to gravity in like normal units, not special American units. You know that we're the only country left. There used to be 3 countries. Now there's only us. So, go America! Alright, sorry. And that's why shit happens like our Mars Climate Observer crashes into Mars because, oops, one team was using metric and one team wasn't. Oops, sorry. Billions of dollars. So yeah, this is the acceleration due to gravity. That is 32 feet per second squared. That's our stupid units. Sorry, I'm just going to be very blunt. Sorry. I mean, you know, our number system is based on 10 because we have 10 fingers. Metric system is based on 10. Yes? What's the boiling point for water, not considering pressure and all that kind of shit? Just water?
100.
No, that's
in Celsius. 200.
See, that makes sense.
212 degrees.
212. What the shit's that? Totally arbitrary.
My physics teacher went on a rant about that last class.
Okay. Physics teachers, yes. Yes, they
America
definitely
tried
do.
to convert to metric in like the 1700s. But,
Yeah, it'll
they-
never happen.
Yeah, but what happened was they had like I think it was Thomas Jefferson like contacted like his French ambassador. They were sending the weights over, and he was coming over, but it was captured by a British naval ship because they were at war at the time. So the ship and all the like standard units were lost, so we never converted.
Made it to a little TV series. I had no idea about that. That's nifty. We had a chance, everybody. There is one sign if you're driving on the 15, I think. There's one sign that's in miles and kilometers. Right? That's one of the few things I've seen in the wild. So, do you have to understand any of the physics behind this? No. It's an ODE. What's the order? And is it linear? Why? What's my dependent variable? S, and everything involved with S is to a first power. So powers and derivatives obviously are different things. So it's the second order, but it's linear, because this is not being squared or something, so being to the first power, linear. What about number 6? Let's start it off. So it's ODE. What's the order? Third order. Is it linear? That's not the reason. Cosine x is completely fine. Doesn't do shit to me. Yeah. So, somebody last time asked about this, and let me write this down while I'm thinking about it because it relates to what we're doing here. My kingdom for any paper. Okay. Here is the general nth order linear differential equation. Right? Dot, dot, dot. And then you get let's do a1 of xy plus, a0 of xy equals g of x. Okay. So that is the general nth order linear differential equation, ordinary differential equation. So if I look back at this, is that a function of x? Do you notice how every, you can do it, Jeff, every coefficient is a function of x and x alone. So that's your first realization. Also, I talked a little bit about the fact that this isn't really to the first power because you have a y thing times another y thing. Now, y times dy dx is not dy squared, is nothing. But it's not linear for damn sure. It's weird though. We're not used to these two things. We're not used to dy dx multiplying by y and being something we think about. If I did solve so that the coefficients of the first term was not dependent on y, wouldn't I divide by y? If I made the coefficient of the first term not dependent on y, wouldn't I have to divide by y? And then I would have a 1 over y running around, and that would be obviously not linear. Are you guys kind of with me? So you can't have two y-dependent terms multiplying each other, even if one has derivatives. That is officially not linear. It's weird. It's not like y times y is y squared, and that's not linear. This is another kind of thing. It's y times dy dx. That's even freakier, but it's not linear. Okay.
So in the first one, so
The
number
first one. Wait, the first term.
No, the first.
The first
question.
one?
Yeah, it's linear because y is not being multiplied.
Yeah.
by the derivative.
Well, it's linear because the coefficient of this is dependent on x, which is 1, right? So it's not really dependent on x, but I think you know what I mean. And this is, the y is to a first power. So real quick, comparing that to this, the coefficient of dy dx is 1. It's not dependent on y. And this, it would be like this term here. A0x would be 10x times y. Okay, maybe. Yes.
So if you have like, if you could get rid of that y, right, would it just be fine? Like if it was a y times dy over dx is equal to 0. Divide both sides by y.
Now that gets trippy. That gets really trippy. It's exactly like, let me see if I can come up with an example real quick. You could do it, Jeff. What if I had this? Right? What can x not be?
1 or 3.
1 or 3. What if I multiply that by x minus 1? Don't these cancel?
Yeah.
Is x equal 1 okay now?
It's a whole.
Is x equal 1 okay now? It's a whole. X equals 1 is still not okay. X minus 1 divided by x minus 1 is 1 for everything except x equal 1. X equals 1, 0 divided by 0. What the shit is that? You guys know better now because you've taken Calc 2, for example. You know about indeterminate forms and all that kind of shit. So I guess it's freaky. Are you guys kind of with me? So yeah, it would still be an issue. Yeah. Because y could be 0 and 0 divided by 0 is... Okay. What is it again, Jeff? Alright, so it's an ODE, it's a third order, and it's non-linear. Okay. What about number 7? We already identified it as a PDE. Is it linear? Totally. What's the dependent variable? U, so it's linear. And what's the order? Second order, I love it. Again, we're not going to go too deep into partial differential equations. We will be using partial derivatives to help us investigate ODEs. But we're not going to look at partial differential equations beyond just identifying them as such at the moment. It's not what the purpose of this course is. Okay. Number 8. Number 8 is trippy. Number 8 is nifty as hell. Because the problem hasn't identified for me what the dependent variable is. How could I do something to make it really clear that I mean y is the dependent variable? What would I do?
Divide by dx.
Divide by dx. So if I divide this by dx, we have to do it both ways. Oops, that's dx, Jeff. Go away. There it is. Is that linear? No. So if y is my dependent variable, that means it's non-linear. Right? You can still tell me the other stuff too. It's non-linear. It's an ODE. What's the order? First order. So it's first order, non-linear, ODE. By the way, I really want to make it clear. The fact that something's non-linear doesn't make it bad, doesn't mean it has no solution, none of that shit. It just makes it harder normally. That's all it means. So I want to really make it clear that non-linear doesn't mean, oh yeah, just ignore it. No. We can solve non-linear ODEs. They're just generally harder to work with. That's why if somebody says they got a linear ODE, I'm working on like, thank God. Okay, well, not that it's that much harder, but it's definitely easier. Is everybody with me so far? What if I look at x as the dependent variable? Then I would divide by dy, and I would get this. Jeff, you could do it, buddy. There you go, my friend. Let's see. Is that okay? I think I told somebody wrong, and I'm sorry.
Still no.
Actually, maybe I didn't. Is this okay?
No,
Why not?
it's
Yeah. If I divided by that, I would have a 1 over x piece. So that's also non-linear. It's all the same stuff. Non-linear, first order, ODE. Is everybody okay with that? So you guys have seen expressions like this before, believe it or not. I'm pretty, you might not remember, but that kind of is related to something called the total derivative. Does anybody remember total derivative? It's kind of related to when you make substitutions to solve, like u sub. When you make a u sub, what's the very next thing you do after you identify what u is? Du equals, so if u is x squared, du equals 2x dx. Hey, see, there's no du over dx. There's du over there, there's a dx over there. Do you guys see what I'm saying? We've done this shit before. We just didn't identify. Hopefully, maybe your teacher said it was a total derivative. In which case, you can decide if you want to do other shit to it. You can decide, what do I want to divide by? What do I want to pretend like my independent variable is or my dependent variable? Are you guys with me? A little bit? By the way, real quick, you guys understand y equals mx plus b?
Yes.
Arbitrary. Yes? We could have made x equal my plus b. Easy as shit. We could have totally done that. Slope would have been run over rise. Sounds weird. You guys with me? So, fundamentally, what's the first place you start talking about dependent, independent? Normally it's linear functions. And you say x is the independent variable. Well, no, I could rewrite it so that it's actually the opposite, correct? So on one level, it's arbitrary. But we do have to choose. And that's why later this semester we'll actually see, what if I choose one way and it's linear and I choose another way it's non-linear? Obviously I'm going to solve the frickin' linear. You guys with me? Yeah. And then if the answer wants it to be y equals shit, I'll just solve for frickin' y. Whatever answer I get for x, I'll just solve it for y. Are you guys kind of with me? Yeah. Right. So I know at the moment there's a lot of, we will eventually do, this is what we're going to eventually see. Sorry, that's the way it goes. Okay. What about number 9 there? What throws that off? Yeah, so it's nonlinear. What order? Second order. ODE. Okay. And again, all that means is the approach we take to solve it could be worse. I mean, think about what this really says. Take away the middle term for a second. Even that's bad. Pretend like the middle term's not there. Second derivative of a function is equal to the cosine of the function. Think about that just for a second. Derive a function twice, and it equals the cosine of that function. Do you understand what I'm saying? Do you see how that would be much more difficult, possibly impossible, right? Understand. Now, not every nonlinear, some nonlinear ODEs are stupid easy because they just kind of fit a form. Most nonlinear ODEs suck. Okay. All right, the other side, this isn't really 1-2. I don't know why I call it 1-2. It's like a small bit of 1-2. 1-2 is primarily about initial value problems. I don't necessarily want to spend a ton of time on this. The most important part of this side is about the interval that I was talking about last time. So for example, this guy. Can you guys see if you plug this in, it'll work? Let's see if you guys can see this. What's y squared? 25 tan squared, right? That's y squared. Yes? And what's the derivative of y with respect to x? So what happens? It'd be 5 times secant squared 5x times chain rule 5. So it'd be 25 secant squared, yes? You can do it, Jeff. There it is, buddy. Are you guys all with me? So if I plug this in, isn't this 25 plus 25 tangent squared? Can I factor 25 out?
Yes.
What's 1 plus tangent squared? Secant squared, so then it will equal the other side. Yes? Okay. So verification. You guys should all eat up verification questions. The only issue is going to be, do you remember some forms of differentiation? But differentiation is always easier than integration. Do you guys agree with me? Okay. So the real question is interval of definition. The interval of definition. So here is my solution. Here's my solution. What is the domain of that function? Oh, shit. Let me see. What is the domain of that function?
-1 to 1.
Where does tangent freak out? Because remember, domain is all about throwing out the shit that makes stuff freak out. So the best way to look at any domain question is just, what would make this freak out? What makes tangent freak out?
Zero.
Freak out. Yeah, what input makes tangent freak out? When cosine is 0, when is cosine 0? Pi over 2. So remember the basic, you repeat the damn thing forever, but the base tangent function lives between negative pi over 2 and pi over 2, yes? Which is why inverse tangent gives us reference angles, because it's only allowed to live between negative pi over 2 and pi over 2. It can't go into the other quadrants. Are you guys all with it? Okay. So, and then of course, negative pi over 2 to pi over 2, pi over 2 to 3 pi over 2, both directions forever. There's all these mini intervals where the function exists. The interval of definition for a solution to an ODE can only be one of those. So in this case, did I give us a point? Did I give us an initial condition? No. So you just have to pick one. So obviously the one we would normally pick would be negative pi over 2 to pi over 2. But just to give you an example, what if my initial condition was, so I could pick negative pi over 2 to pi over 2. That could be, no, stop it, Jeff. There's a 5 in there though, right? That was the next level of this. So normally tangent doesn't work from negative pi over 2 to pi over 2. What input would make the inside pi over 2? Yeah, so it's negative pi over 10 to pi over 10. There you go. So I could pick negative pi over 10 to pi over 10. What if the problem had given me an initial condition? Something like this. Y of pi, let's say y of, pi over 4 equals 2. Sure. Is this interval appropriate considering this initial condition? Nope. I would have to keep going. So what's the next interval after this one?
3 pi over 10.
Pi over 10 to
3 pi.
2 pi over 10, right? Oh, I'm sorry, how wide is this interval?
2 pi over 10.
Yeah, so it's pi over 2 pi over 10. So the next interval would be pi over 10 to 3 pi over 10. Is that good? Is that the one we want to use?
Yes.
Does it include pi over 4?
Yes, it does.
Yeah, why?
Because 3 pi over 10 is greater than pi over 4.
Yeah,
It just falls in
and it's
between- it
also,
falls
and
in
pi over
between
4 is
the
also
two.
greater than pi over 10. Okay. It's kind of a gross example, but you see, if I give you an initial condition, you can actually select the correct interval of definition. Let me stop for a minute. So the idea of domain only cares about what are all the areas where this function exists, has outputs, right? Interval of definition has to be one of those intervals, and I can pick the right one if I know the initial condition. I know where I live, right? So if my initial condition is dependent on pi over 4, I just have to find the interval that actually contains pi over 4. That would be the interval of definition. Okay, let me stop for a minute. Okay, maybe. So all of these are basically the same idea. We've done this exact problem, maybe not. We've done a problem like this, I believe. Sorry, this guy. Does this have any issues? What's this guy's domain? Are there any x's you're not allowed to plug in? Nope. So an interval definition here would be negative infinity to infinity. Actually verifying that that's the answer, you guys, again, should just eat that shit up. You just take the appropriate, how many derivatives would you need to take? 2. Plug it in, make sure it works. Yes? Okay, I like it. Now, one little thing that's interesting, here's the same exact equation, differential equation. Do you agree with me that y equals 0 is a solution?
Yes.
Yes. Because if y equals 0, y prime is 0, y double prime is 0, so 0 plus 0 is 0. Okay, I like it. You guys all with me? So, very often, our ODEs will have a particular solution. It'll have some, like, we saw some the other day, C1 sine x plus C2 cosine x, right? That would actually capture the trivial solution. There could be a trivial solution of 0. There actually could be a trivial solution of 1. so forth. So let me make one little change here. If I made this change, the trivial solution would be y equals 1, because what's y prime? Y double prime? Y equals 1. Okay. So very often you'll be able to see what the constant solution to something is going to be just by observation. Now this one's interesting because the interval of definition, does this have any issues anywhere? Y equals 0. No. X can be anything, right? I just need y to be 0. So the interval definition again would be negative infinity to infinity. Okay. Now this one's very obvious. What's the domain of this function? X can't be 1/11. That's the way I would write it, right? You could write an interval notation, but that's crazy. But, so what is it? Give me one acceptable interval of definition for this differential equation.
3 to 4.
I love it. So it could be a slice of 1. So the domain would be negative infinity up to 1 union with 1 to infinity. So yes, one possible valid interval of definition would be 3 to 4 because that lives inside of here. Another one could be an entire one of these. Okay, it just has to be continuous, its own continuous set of x values. Okay. Yes.
What do you have verifying problems that like all words like
Oh, if it says verify, that's assuming it's true. You're supposed to verify. The point normally is after that. Yeah. Now, if it said check to see, then it could work or not. Yeah. All right. Okay. Now again, this is all a little unsatisfactory because we're still not talking about how to solve these things. I understand. Okay. Sorry guys. That's abrupt, I know. It goes down nice and then it comes up like bam. It sounds like I hit the bar. Okay. I gave you, on that sheet we just did, I kind of gave you at the top the definition of a solution to an ODE. The really neat thing is, a solution of an ODE is that any function, you can either say this phi or phi, which is not faux or fun. Phi, so what I normally say is phi. So phi is interesting because it's the Greek letter F, which is nifty because when we say function, we normally think F, and now we're trying to make it even more like ooh, so we make it a Greek letter F. On an interval I, and this is really just saying how to check your answers. When you sub it into the ODE, it reduces to an identity. I mean, that's how we check solutions in algebra, for example. We just plug it in and see if it becomes an identity. Blah, 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 blah. So that is the definition of a solution to an ODE. Oh, I do want to, let's look at a specific example. Yeah, so like, what do you guys think about this here? Oh, I put the wrong thing. Let me make it this way. Sorry. There. So let me rewrite this a little bit. So this is x times the derivative of a function equals the negative of that function. So what do you think might be an answer to this? Cosine?
Yeah, because it's gonna switch to a negative, the derivative. will be
But there's that x piece though.
0.
I love it. So one answer, I love it. This is what I was hoping would happen. One answer is the trivial solution at y equals 0. Kick ass. Right? If I make y equals 0, that is trivially true. Right? What do you take the derivative of? Now, look at by observation. This says there's a function whose derivative loses a power of x. Do you see that? Because what do I have to do to the derivative to make it become on the same level as what the function was to begin with? Don't have to multiply it by x. So somehow it lost a power of x. So isn't that basically any? Yeah, but there's a negative though. So let me throw this at you. What about this? What's the derivative of that?
X to the negative
It's
side.
negative 1 over x squared. And what is x times that? Okay, so isn't x times that equal to the negative of what it was? Okay, good. So that is a solution to this. Right? Is that the only solution to this? So let's try it. Okay, so let's try, what if I put, instead of that, let's make it more general, let's say, what about c over x? And of course, why does it feel like this is probably going to work? Because what do constants normally do when I take derivatives? They just sort of come for the ride, right? So they're still there. They were there at the beginning, they're there at the end. So the derivative of this would be negative c over x squared. X times this would be negative c over x, which is the negative what it used to be. So y equals negative 1 over x is a specific solution. It's a particular solution. Y equals negative c over x. Sorry, why did I put that there? Y equals 1 over x is a specific solution. Y equals c over x is the family of solutions. Okay, I like it. So very often we're going to find the family solutions. And you've done this. You've done this in 180. Every damn time you did an indefinite integral, you got a family of solutions. And of course, how did you figure out what the c was? I had to give you more information, right? So the same thing's going to happen here. We're just going to have to be much more careful about our constants. We saw the other day, so let me bring this back at you. Before I go too far, what would be an interval of definition for this? It would be anything that does not include 0. Okay. So remember, let me bring this back. Some of you guys were remembering this. That guy. Does anyone remember what the actual complete solution was for this? Yeah. So it could be any constant times sine. Do the constants have to be the same? And that's why I put different subscripts, right? Those constants do not have to be the same. If I have a series, if I have a bunch of functions that all solve some given ODE, then most likely, I can at least do this. If not, put constants in front. Okay. So we're going to have, it's kind of like the next level of plus C. We're going to have several constants that are all different from each other. So we have to give them, the default is just do C1, C2, C3. Okay. I like it.
But that doesn't always happen, right?
No.
Okay.
Yeah. In fact, let me see. I have an example coming, not quite yet. There's a nifty one coming up. By the way, what's the trivial solution to this?
0.
Y equals 0. Does this capture that possibility?
Yes.
Mm-hmm.
If I make C1 and C2 both 0. Good. So we will look at situations where that doesn't work. There will be an answer, a trivial solution that the general solution does not capture. Which means officially there would be more than one solution. Would you agree that this definitely seems to be the only solution? Or it would be understandable if you said, I'm not really sure, Jeff, maybe there's more solutions. So I agree. But this does turn out to be the only solution to this. So the beautiful thing is we have this theorem we're going to go over today that tells me when a solution exists and when that solution is unique. You guys all with me? this theorem relies on much higher level mathematics to be proven. This is unfortunate, but this just happens. The way we've decided to teach mathematics, very often we just go, oh yeah, this is true, this will help us. Why is it true? Well, you gotta take, math 527 to understand it. So just trust me. So what I'm gonna try to do is just show you some examples where it fails, which is normally the best way to kind of investigate why it makes sense, but it's still not a proof. Are you guys kind of with me? Okay. So we're going to talk about that later. One thing I want to talk about is explicit versus implicit. Does anyone remember this? This has already come up earlier about implicit differentiation, everybody's favorite. Actually, everybody's favorite is probably related rates. Do you guys remember those days? Related rates. The gravel makes a cone. Oh, sure it does. Whatever. What the hell does this mean? Explicit versus implicit. Can somebody give me an example of an explicit equation? What the shit does that mean? You guys remember? What does that mean? Yes.
Would it be like a y equals just in terms of
Totally.
x
So
versus-
explicit would be y equals x squared plus 7. That's an explicit function of x. Implicit must mean some statement that is currently not solved for y, but I prefer it to be something that you cannot solve for y. So the easiest example of that we normally give is a circle, right? I cannot solve that for y without using more than one function, correct? I can solve it for y, but I get a plus or minus. Oops, can't really solve it for y then in one concise statement. Are you guys with me? Now this is kind of silly because I can solve for y. Can anyone here, if you can do this, teach me. Can anyone in here please solve this for y? Here we go, there we go. All right. I love it. That's the question, why? Could I find, now listen, if I was really, really evil, which I'm really close to, I'm trying to get that next level. I got to level up, I'm almost there. I just got to smith something, it'll be good. If I asked you to, you could all find dy dx. Yes? This is gross. But isn't each piece? Each piece is relatively easy, which is the key to mathematics. This is not one problem, this is many easy problems. This is a lot of writing, but it's not hard. It's just like a lot of writing. So I would never give you this damn thing. It's just busy work at this level, right? But y'all could. Could you also solve, so if you solve for dy dx, could you also solve for dx dy? Yeah, of course, you just turn this shit over, right? So we talked about earlier. Okay, I love it. So we could do that. So that's what explicit versus implicit. So what's that have to do with differential equations? Jeff? Why are you bringing this back? Jeff? Well, because, I'm sorry, I don't know if somebody was copying that down to try it at home. I'm sorry. For example, here. Can you solve that for y? All right. So before I see smoke coming out of your ears, no. Whatever you try to do is going to make the other piece of y caught in something, correct? It's like a gopher. You hit one, it pops up another one, right? Yeah. So if I have this differential equation, let me see. I'm not going to remember this. You could pick the paper up and take it with you, John. I could totally do that. You can do it, buddy. I kind of wrote it out on purpose, so it sort of looks like dy dx plus function times y equals 0. Now this function is not just a function of x, correct? So that's why this is not linear, is it? But this is an example of just being not linear doesn't mean a damn thing. It just means it could, more than likely, it's a little harder. Now I agree, this would be disgusting. Trying to solve this without, now that's the solution. If you plug this in there, it works. You guys kind of with me? So this is just an implicit solution to a differential equation. That's all. So just wanted to show you that some solutions to some differential equations can be implicit, meaning you cannot solve for y. No big deal. Math doesn't really give a shit about that. We just focus so much on y equals, and we make it seem like that's some amazing place to be. No, this is a solution to this. I don't care. Okay. Maybe. Okay. Yeah. Also, what about this? This solves this. It's kind of related to the one we just did a minute ago. Can you guys see this? It's if I multiply the derivative by x, it basically becomes 4 times the original, and that's exactly what taking a derivative here does. Does that make sense? Okay, maybe. So it makes sense that that is the solution to this, right? So is this a solution? Does that solve it? Yes, that's a choice of C I've made, correct? I can make any choice I want to for C. What if I make C 0? Is that cool? Totally, yeah. So a C can be anything it wants to be. I like it. So is this a solution to this? Yeah, Jeff. So is this a solution to this? Is that a solution? All day. All frickin' day, right? Of course it's a solution to that. Because the equation doesn't give a shit with the coefficient. Now, real quick, the most important thing when you have a, what is this called again? Piecewise. I like it, not Pennywise, none of the floaters. When I have a piecewise function, what is the most important thing? It's not always the only thing, but the most important thing to check for a lot of piecewise problems is it continuous at the point of transition, right? So this is a solution to that differential equation because it works, but more importantly, it's continuous at 0, correct? If it was discontinuous at 0, that would be a major problem. Okay, maybe. So there is a problem in the homework that basically is directly the same as this problem, just a little worse. But now you see what to kind of check. Oh, here we go. This is beautiful. By the way, I want to let you know this. The first chapter is kind of like just full of this overview, so it feels like I'm just like throwing a lot of shit at you. Once we get to chapter 2, each section is kind of very well defined. Chapter 1 is very kind of broad. They all interconnect. There's strict definitions, but there's a lot of kind of stuff happening on the sides. We will focus a bit once we get to chapter 2. Somebody remind me, if I have a function that looks like this. Oh, shit. Can you take its derivative? I affectionately refer to this as FTOC 1, Fundamental Theorem of Calculus 1. Remember there's 2 parts? First part is related to the derivative of integration. The second part's related to how to actually do a definite integral f of b minus f of a. Like big ass f of b minus big ass f of a. You guys kind of with me? You guys remember this f? I don't know if your teacher called it FTOC, but I do. Yeah, this one's nice, right? This is beautiful. So you would hope that the derivative of an integral would somehow just cancel, just like cube rooting a cube root. Cubing a cube root, there it is. Those cancel because they're inverse operations. So this one's a little more complicated because you've never seen a freaking function of x like this, but there's an x inside the function, so that is a function of x. So when I take its derivative, you get g of x. I'm not going to reprove that, right? Okay. So there are differential equations that have integral function answers. So they would be integrals we cannot do. So eventually we're going to, so remember, what about this? E to the x squared. Can you integrate that? Directly. Can you integrate that directly? Could you integrate that using, I don't know, Taylor series? Could you get a series representation of the answer? Do you want to? Too bad. We go. All right. So sorry. Some differential equations, their solutions are integral functions. Because can I integrate in a closed fashion every function? No. Do you guys remember what those are called? Elementary functions versus non-elementary functions. Okay. So the integral of e to the x squared, I cannot integrate that directly. I have to use a infinite series to do this. Okay. Blah, 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 blah. So real quick, just to be careful, what if I did one little different thing here? What if I had that? What would the derivative be? All right, so real quick, go with me. If I have sine x squared, like that, what's its derivative? Good, so derivative of sine is cosine, and then of course you have chain rule, right? So the derivative of the integral of that is that evaluated at the functional exponent, the functional limit, sorry. You guys with me? So it is this. That's the definition. Just like what's the definition of the derivative of sine? Cosine. What's the definition of derivative of an integral? The inner function evaluated at that x limit. Then, of course, I have chain rule, because the inner function is x squared, so then it would be that. So there will be some problems in this chapter 1 homework. This is verify the solution to this differential equation is this. You take its derivative, you throw the stuff in, you make sure that it works out, there you go, right? You just have to remember how to differentiate intervals. Okay. I like it. Oh yeah, this is over here. Good, okay. So, we're finally ready to actually get into section 1-2 officially. Yeah, we've done so much. The great thing about section 1-2 is it's everything we've done, except now they just officially bring in initial conditions. And so the interval and definition will be a lot more defined, like we were talking about earlier. Yeah. So if I have an initial value problem, that's what that stands for, an initial value problem. That's different from a boundary condition problem, so we'll do one of those too. So let me see. Yeah. Okay. So for example, if I have an nth order, nth order ODE. And it's subject to, and actually, yeah, where would this go? Where would this end, by the way? -1, yeah. Because that's already the nth, so it'd be dependent on all the lower level. Okay. And then I subject this to several initial conditions. So like y of x naught equals c naught. Let me use the same notation I used. That's better, Joe. Y naught. There we go. And then y. I can even do another condition like y prime, which you see often. Y prime of x naught equals y1, so forth. Okay, so right now this is very abstract. Mostly we're going to be concerned with second and first order ODEs to begin with, right? Then we're going to talk about how to kind of like ramp up what we're doing to handle higher level. So this is an nth order, there's a lot going on. The solution to this will involve no C's. I'll be able to solve for the C's, the parts. So let's do an example. So if I had, let's see, yeah, y prime equals y, subject to y of 0 equals 2. All right. So you all know what this is. What's the solution to this? This is one ones we talked about last time. What's the solution to this?
E to the x.
Second?
E to the x and 0.
Be more general.
Oh, c e to the
Yes. Right? Again, that constant will come for the ride. Can you always just throw a c in front of something? Hopefully now you understand you can't always do that. We're going to see an example here in a minute. Okay. But for this one, it's just got one part of it. The constant will come for the ride, so it's going to work out. Very easy little DE. Not too much going on. Y of 0 equals 2. How do I get c? Yeah, the output's 2 and the input is 0, so therefore c is 2. Crazy shit, right? Now, an interval of definition for this, of course, could always just be all real numbers because e to the x has no issues anywhere, right? What if the initial condition, so this leads to this solution. What if the initial condition was y of negative 2 equals, what did I say, negative 3 or 3? Doesn't really matter. Yeah, 3. Same idea, right? So now it's going to be 3 equals c e to the negative 2. So what's c equal to?
3e squared.
3e squared, I love it. So you could make it 3 over e to the negative 2, and then it flips up. Right? So then what's the solution? Y equals 3e squared ex. And how do you make that better? Careful.
X plus 2.
Yeah, add exponents. What's really, I want to point out something very kind of like side notish. The way it's written here, isn't this a vertical stretch? Do you guys remember your translations of functions? Isn't this multiplying e to the x by some number? Isn't that a vertical stretch? Okay, what's this?
Shift.
Shift. Which direction? Back 2. I love it. So this is saying that if I shift this function back 2, it's the same as multiplying everything by 3e squared. It's just a little side note. It's kind of interesting the way that these bases work. Okay, I like it. Okay, maybe. All right, so that's pretty much what I would hope you would expect to have happen. If I give you information, you should be able to solve for whatever unknowns you have. Blah, 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 blah. Yeah. Yeah, there you said it. Let's see. Oh, here we go. Beautiful. Okay, here's an exceptionally funky situation. There. So for this, yeah, this is nifty. First question, is that linear? No. So the method to solve it, we'd have to create a method to solve this that would most likely generally be harder than linear. Okay, so there is a method to solve these kind of differential equations. The solution turns out to be this. One solution is this. Is that obvious? Good. If somebody said yes, I'd say, please show me afterwards. And Jeff, it's obvious. What's the other solution, of course? The one that you should always kind of be primed to look for? 0, right? Is that the 0 always the other answer? No. I showed you earlier how it could be something else. It depends on if there's a number here or something. But in this case, if I make y 0, everything's 0. That's why we call it the Trouville solution. You just make everything 0. It works amazing. Does this capture 0? Does everybody understand what I mean by that statement? I know I don't use purely technical terminology all the time. This does not capture the option for y to be 0. There's no value I can put in for c to make this 0. Correct? I love it. And you can't go, well, if you make x infinity. No, get out of here. Can't do that for one. And number two, x can be anything. You can't just make it a single, it's not a constant. So this is an example of a ODE that has two solutions distinct. There's not a unique solution to this. There are two solutions to this. You guys with me? Okay, I like it. Very interesting. Yeah, so what if I subject this to an initial condition? What if I say y of 0 equals negative 1? Can you please tell me what the answer? Could it be this answer? No, right? So once I give us an initial condition, I can start to see which of these options actually works. Now, obviously, if I would have said y is 0 equals 0, what would have been correct? This one. If I would have said y of 2 equals 0, this one, because that's where y equals 0. Because can this ever be 0? No. Okay.
So if you have like an equation and you know, or you find out that it has more solutions, right? Would you only give us that after, or do you have to find all the solutions first? Or
Yeah.
yeah.
So in this example, you want to know ahead of time what all the possible solutions are. If you didn't even write this down, and you didn't realize that's a possible solution, and I gave you an initial condition of y 0 equals 0, you're going to freak out trying to get this to work. When I put a 0 in, how do I make that 0? Can't. Right? And dear God, nobody, it's going to hurt me to write this. I don't ever want to see that shit. Right? I once had somebody who could just not stop doing this, so I said, put BFN, big frickin' number. Right? Because you can't plug infinity in somewhere. So can you just take a moment, figure out what the function answer would be if that was the initial condition? You could do this. So when the input's 0, the output's negative 1. Yeah, so C would have to be negative 1. I love it. So the answer would be 1 over x squared minus 1. What's the domain of that function? So the domain, if I write it in interval notation, which is actually a really good way to write it, so you can see all the parts that are possible, be negative infinity up to negative 1, right? Negative 1 to 1, 1 to infinity. Is that cool? I'll get many people forget the poor little middle dude. Poor little middle dude. Sure. That would really suck here, because what's the correct interval of definition given this IVP?
The middle one.
The middle one, right? So don't wow, poor little dude. So look at real quick. I've always thought about this as saying skip. So it's negative infinity to infinity, skip negative 1, skip 1, right? Just make sure you get everything. You're only skipping the parts that don't work. Does that make any sense? You guys with me? So what is it? I'm sorry, you already told me. So the correct interval of definition would be negative 1 to 1 because our input from our initial condition is in there. So our solution only exists on that interval. Outside of the interval, I have no idea what's going on. Right? Okay. Maybe. So what if I made the initial condition... Oh yeah, I already said this. Shoot, I already said this. If the initial condition was, of course, y of 0 equals 0, then the answer, of course, would be y equals 0. Right? That's kicks ass. So a little work to do. Okay. So you really, in general, when we start solving differential equations, one of the very first things we're going to do is what makes the thing 0? What's the trivial solution in this case? Right? Okay. All right, so here comes this theorem I was talking about earlier. Okay. This is called the existence and uniqueness theorem. Because math people were very creative. And we said, oh, this theorem talks about if something exists and is unique. We'll call it the existence and uniqueness theorem. If you want to, you could Google the proof of the existence and uniqueness theorem and just see the levels of mathematics you'll need under your belt. A lot, yeah. So basically, here's what this says. if I have a region in the XY plane, so let's say I have the XY plane, and I have a region R, define, let me use the same, yeah, sure. So I have this rectangular region, and if you've, I'm going to say this a few times, and I'm really sorry, throughout the whole semester. If you've taken Calc 3, you're very used to this, right? Because the next step from Calc 3 would be what lives over this. These are input ladder, but that's not what we're talking about here at all. Okay. So we have this region in the XY plane, and it contains the point X naught, yeah, Y naught. Okay, that's all we know at the moment, right? Okay, I like it. Oh yeah, good read, all right. If, no, given the initial value problem, let's just stick with, let's see, yeah, let's just stick with this here for the moment. Dy dx equals function of x, y. Given this initial value problem, if the function is continuous in a neighborhood, let me say across a neighborhood. All right, let me stop for a minute because I love when I first say the word neighborhood for people in mathematics. Have you guys ever, I'm sure at some point, I can remember, yeah, if you did epsilon delta, I would talk about neighborhood. A lot of people skip epsilon delta and 180. Anybody ever heard the word neighborhood in mathematics? No? So in a neighborhood just means some interval containing that. So the neighborhood here could be this circular region, and it could be big or small. It just has to be some neighborhood around there. Oh yeah. I brought this in too early. I love it, Jeff. Not the neighborhood yet. I was so excited about the neighborhood. If the function is continuous on R, that means that you're guaranteed a solution exists. It could be 1, it could be 2, it could be 80 billion, it could be an infinite number. I'm gonna get this a little more formalized in a minute. If the partial of f with respect to y is continuous, then that solution is unique. Now, the interval of definition for the solution, that's where the neighborhood comes in. By the way, I'm sorry, I forgot. Here. This guy is important because it is basically the initial condition that I'm given. So this would be y of x naught equals y naught. Okay. So the interval of definition would be some neighborhood around x naught, y naught. Now this is, if any of you are going to go very far in mathematics, right? And I always secretly hope, I'm like, please, dear God, don't let me be the reason somebody gets turned off to math. But if anybody's going to go further in mathematics, you get to a lot of proof classes. I would love to create a course that would be I took a course that was a history of math and a proof class together. That was neat. And that would be awesome to teach. But we're not going to prove this, because like I said, you need quite a bit higher level mathematics to be able to prove this. The interval definition would just be some neighborhood. Jeff, you need a lot more letters. Okay. Around x naught y. We're guaranteed that that exists, that a solution exists it's unique, and the interval definition would be some neighborhood around x naught, y naught. So, for example, I wish I would have kept it up here. That problem we just did a minute ago. Where'd it go? Shoot. It's right there, yeah. So this problem we did a minute ago. It was the DE was this. So if I do this, what is f of xy? What's f of xy?
Minus 2x.
Yeah, minus 2xy squared. Is that continuous on some region? Yeah, is it discontinuous anywhere? Nope. Now here's the part that some of you guys have never been shown how to do. But if I treat x like it's a constant, that's all partial differentiation is if I only let y change and I hold x constant, so that is a constant now, what is the derivative of this? Negative 4xy. So when we solved this, we didn't really solve it, but when I told you what the solution was, there were two main options. But the minute I'm given an initial condition, I got a unique solution. It was either y equals 0, or it was y equals 1 over x squared plus some number, right? So from this, I investigated f, it's continuous. I investigated the partial, it's continuous. I'm guaranteed a solution exists, and that is unique. If either one of these fail, anything can happen. I need you to understand, it's not an if and only if situation. If either one of those fail, the theorem's like, I don't freaking know. Anything in it. You can get an infinite number, you can get no solution. I have no idea. This theorem just says, if both of these are true, you're going to get one solution that's unique. Say again. Oh, what's the name of this theorem?
But you're just saying that if this fails, what makes it unique?
Oh. This part tells you that something exists, and this part tells you that it's unique.
Is there an overall name of the theorem?
You're going to love it. You ready?
Yeah.
It's the existence and uniqueness theorem. Because math people are special. All right. I'm basically out of time, but... Right? Yes, I am. Time flies. Section 1.3, I need you to understand. The entire chapter 1, we're not solving any DEs. Section 1.3 gives us a few physical situations. Some of them kick ass, and let's see if I get a revolt. If anybody wants to revolt, I understand. But really quickly, just really quickly, because I need you to see this. One of the coolest things, If I have an inductor in a series, so if you've never done any electrical circuits or anything, you're fine. But there's things called inductors, things called capacitors, and then of course everybody knows resistors, right? It's futile. Current is just the motion of charges, and charges we call Q. So when I have a inductor, it can hold a certain amount of voltage. Voltage can drop across it. Now when you get into the real physics of it, it's really nifty. Then I've got this. How did I write this? Where'd it go? Oh yeah, okay. Jeff, you got it right there. That of course is just the resistor, what it does, right? So it's the level of resistance times the current going across it. That's the voltage drop. And then I've got a capacitor, which is the simplest little dude. If I add all these together, and I put a battery into this circuit, the amount of energy the battery gives, so this would be the voltage the battery is providing, would equal the loss across all of these. So if I add all of these up, so I just want to show you, and I know, I'm sorry I'm pushing it here. You guys are all like, we'll let it go today, but this is a natural place where a completely, what order DE is this? Is it linear? Yes, it's the second order linear differential equation that describes the charge moving across a circuit. So if I can solve for Q, given certain values of this, I can then do some stuff with it. I can set things up correctly so I can get the right thing happening that I want to have happen. So that's a beautiful physical example of differential equation showing up. That's plenty, I'm sorry. So next time, I am going to try to remember to post something specifically about engineering, because I know a lot of you guys are engineers, so there's nifty stuff that engineers do with these. And next time we'll talk about direction fields.
We just took the calculus-based version of the physics course that does the electricity.